Hello everybody. Today I want to talk about constants and how you can use them in your Go applications. Now there are several things that we need to talk about with constants, so like we've been doing, I want to break this down into several categories. The first thing that I want to talk about is how we're going to name constants in our Go applications. Then we'll talk about typed constants, followed by a discussion about untyped constants, and we'll talk about the differences between those two and the options that each one gives us. And then we'll talk about a method of generating constants that are called enumerated constants. And finally, we'll end our discussion by talking about enumeration expressions, which are going to build upon the concepts that we're going to talk about in that first enumeration discussion. The first thing that I want to talk about is how we're going to name our constants. So all constants are going to be preceded with the const keyword that's going to let the compiler know that that's what we're trying to work with. Now, if you've come from other languages, you might be expecting that we're going to name our constants something like this, where we're going to have all uppercase letters and separate the words with underscores. The problem with that is if we do that in Go, then the first letter is going to be uppercase. And as you remember from our discussion on variables, if we've got an uppercase first letter, that's going to mean that the constant is going to be exported. And we don't always want that. So instead of this, we're actually going to name our constants the same way that we name variables. So if we had a variable that we wanted to call myConst, and we didn't want to export it, then we would start with a lowercase first letter, or in other words, we would use camel casing. And if we did want to export this symbol, then we would simply change that first character to uppercase. Now, assuming that we're going to be working with an internal constant, then we're going to switch this back to a lowercase first letter. And then let's talk about how we can create what's called a typed constant. Now, a typed constant is created very similarly to a typed variable. So we can start with the const keyword, then the name of our constant, and then we're going to list the type of the constant, and then we can set it equal to a value. Then if we want to prove that that worked out the way we expected it to, then we can go ahead and print out the value and the type of the constant, and we will do that by using this printf statement here. And then when we run this, we see that the constant is in fact created. It's got the value 42 that we assigned, and it's got the type that we assigned to it. Now, the reason it's a constant and not a variable is it has to remain constant. So if we tried to do something like this, change this to the value 27, then the compiler throws an error because we're not allowed to change the value of a constant. Another characteristic of a constant is that it has to be assignable at compile time. So for example, if I wanted to have a constant that represented the sign of pi over 2, then I might be tempted to do something like this. I'll create a float64 constant, and I'll set it equal to the result of the sign function from the math library, and I'll pass in 1.57, which is approximately pi over 2, and then I can run this, right? Well, the problem with that is in order to determine the sign of that value, that actually requires the function to execute, which is not allowable at compile time. And so you can't set your constants equal to something that has to be determined at runtime, and that includes things like setting it equal to flags that you pass into your application when you run. If you're going to do that, you can't use a constant to store that value. Now, constants can be made up of any of the primitive types that we talked about in the last video. So if we have this example here, we've got an integer constant, we've got a string constant, a floating point constant, and a Boolean constant. And if we run this, we see that all of those print out exactly the way that we expect. We've got the integer, the string, the floating point value, and the Boolean value. Now, in an upcoming video, we're going to talk about the collection types. And the collection types are inherently mutable. So for example, you couldn't create an array and declare that to be a constant type. Arrays are always going to be variable types. Now, another characteristic that constants have in common with variables is they can be shadowed. So if we create a constant at the package level, and let's just make this an integer 16 and set it equal to the value 27, then we'll delete these guys and also these guys. Now we've got a constant called a declared at the package level that's an integer 16, and then we got a constant in the main function that's also called a, and it's an integer type. So if we update this printf statement to print the type of the variable, we see that looks like I need to print my variable twice. We see that the inner declaration of the constant wins. So not only can we change the value of the constant, but we can also change the type because the inner constant shadows that outer constant. And we can prove that by commenting this line out, running again, and we see that the package level constant wins. So you want to be a little careful here because if you're going to reuse constants, it's going to feel like those values are changing. So I wouldn't recommend that you take advantage of this, but if you do get into a situation where constants aren't evaluating the way that you expect them to, this is one possible reason. Now, when we're working with constants, they work very similar to variables when we're using them in operations. So if we bring this line back and set it equal to 42, And then what I want to do is declare a variable. So we'll declare a variable b as an integer and set that equal to the value 27. And then we can do a plus b. And let's see what happens when we do that. So if we run that, we in fact get the ability to add a constant to a variable, and the result is going to be a variable. And so since the constant and the variable are of the same type, we can perform the addition operation on there. Now if our constant is of a different type, for example if we made variable b an int16 and run this, then we get exactly the same failure that we get when we try and add two variables of different types together. Now so far all that we've been talking about are these typed constants, where after the constant name we list the type. But we don't have to do that. We can use the compiler's ability to infer the type for us. So let's just go ahead and do that with this example here. When we run this, we see that the constant a is inferred to be an integer with the value 42. Now given that the compiler's inferring the value, what do you think is going to happen if we do something like this? If we restore that previous example, where we're going to add this constant to an integer 16. Well, in fact, in this case, the operation succeeds, which might be a little bit confusing. But the reason that works is because what the compiler's actually doing when it sees this constant is it's basically replacing every instance. So the way the compiler sees this program is it sees it like this. So since we're taking a literal 42 and adding an int16 to it, that 42 is interpreted as being an integer 16. So the compiler doesn't say, oh, constant a equals 42, that's an integer and always an integer. Instead, the compiler is going to look for every time that we use the symbol a, and it's going to replace that with the value of the constant. And so we can do these implicit conversions when we're working with constants, which is something that we can't really do when we're working with variables. The next thing that I want to talk about are what are called enumerated constants. So let me go ahead and start that conversation out by wiping out what we have here, clean up our code just a little bit. And then I'm going to do this at the package level because this is where I've seen these most commonly applied. You could do these in a function level if that made sense in your application. So I'm going to declare a constant a, and I'm going to have that as an untyped constant, and I'm going to set it equal to this special symbol called iota. So when I run this, you see that a is evaluated to have the value 0, and it's inferred to have the type integer. So what is iota? Well, iota is a counter that we can use when we're creating what are called enumerated constants. So in this example, having an enumerated constant isn't terribly valuable. But one of the things that I can do with constants is I can actually work with them in a constant block like this. So when I'm doing this, I can create another constant, set that equal to iota, and another constant, and set that equal to iota. Now let's go ahead and clean up this because we already know what the type is going to be, so we don't need to be printing that out. And then let's print this command out 2 more times, switching to B and C. So now we're using iota 3 times, and when we get the result, we actually see iota is changing its value as the constants are being evaluated. So the first constant that's assigned has the value of 0, then 1, and then 2. Now another special feature that we can take advantage of with iota is that if we don't assign the value of a constant after the first one, then the compiler is going to try and infer the pattern of assignments. So in this example, we would expect to have an error because B and C don't have a value assigned. But since we've established a pattern for how to name the constants in this block, when we run, we actually get the same result. And that's because the compiler is going to apply the same formula. So it's going to apply B equals iota and C equals iota for us. Now, that value of iota is scoped to that constant block. So if we create another constant block, and in this case, we create a constant called A2, and set that equal to iota, copy this line, bring it down, and print out the value of A2. Then what we're going to find is iota resets to 0. So iota is scoped to a constant block. And what that lets you do is you can actually create related constants together, ensure that they have different values, and then if you have another set of related constants, you can start another constant block and ensure that they have unique values, but allow duplication between the values in one constant block and another. So what's an example of where you might use this? Well, let me just drop in this simple application. And what we're doing here is we're setting up a constant block where maybe we're trying to store the specialty of veterinarians in a veterinarian clinic. So a veterinarian could be a cat specialist or a dog specialist, or maybe we can take a snake specialist too. Now, as you can see, inside the const block, I'm setting the cat specialist equal to iota. And then in the main block, I'm creating a variable and setting its value equal to cat specialist. So if I check to see if the specialist type is a cat specialist, then I in fact get the value true. Now that works just fine. And this also works if I, for example, use a dog specialist, assign that specialist type to be a dog specialist, run that, then that's going to work out just fine. So everything looks really good here, right? And this is a very common use for enumerated constants. However, one thing that I would warn you about is what happens if I declare this variable and don't initialize it to a type. Well, if I check to see if it's a dog specialist, I get false, which makes sense. But remember, what is the initial value of iota? Well, the initial value of iota equals the 0 value for an integer. And so in fact, even though we haven't specified a specialist type, it does show up as the value cat specialist. So what do we do about this? So there's a couple of approaches that we can take here. The first is to use the 0 value of the constant as an error value. So we can set this equal to error, then we don't need this statement anymore. And now, when we check to see if the specialist type is a cat specialist, we get the value false because cat specialist is equivalent to the integer value 1, which is no longer the 0 value of the integer. This is a very valuable approach if you want to check to see if a value hasn't been assigned to a constant yet. So you can specify an error specialist, and then you can check to see if that value is set equal to the 0 value of that constant. And if it is, you can handle that error because presumably you expect that to be initialized in some way. Now, if your application guards against that, and there's no reasonable way for this to happen, then you can take advantage of this underscore symbol, which is goes one and only write-only variable. Now, what's the value of a write-only variable? Well, with iota, we have to have a 0 value. We always have to start with 0. But if we don't care about 0, then we don't have any reason to assign the memory to it. So we can use this underscore symbol, and we'll see this in quite a few places in our Go applications. And basically what that tells the compiler is, yes, I know you're going to generate a value here, but I don't care what it is. Go ahead and throw that away. So if we run our application again, everything works just fine. But in this case, we can't actually get at the 0 value of this constant block. Now, the ability to create lists of enumerated constants with iota is very valuable, but things don't actually stop there. And the reason is, remember, the value of a constant has to be able to be determined at compile time. But there are some operations that Go is going to allow us to do. For example, we can do addition. So if we do this and run, then we get false again. But what happens if we print out the value of cat specialist? If we do that, and we're going to have to remove this line, then in fact, that expression got evaluated. So the first line, line 8, is evaluated to iota plus 5, which is 0 plus 5. The next line, cat specialist, iota increments, and the formula repeats. So cat specialist is equal to the value 6, dog specialist is 7, and snake specialist is 8. So this can be valuable if you need some kind of a fixed offset. Now, a common use case for this is to use the bit shifting operators, because anything that we can apply to our primitive type, we can apply here as long as it's not a function expression. So we can do addition, subtraction, multiplication, and division. We can do remainder operations. We can do the bitwise operations. And we can do bit shifting, which is one of the more interesting use cases that we can take advantage of. And the reason is because we don't have the ability to raise to powers, because raising to powers in Go is a function in the math package. So we can't do that in our constant evaluations. But by bit shifting, we can raise things to the power of 2, because every time you shift a number one level, you're actually multiplying it by 2. So we have this example here, and I actually stole this from the Effective Go article on golang.org. So what we have here is we have an example of a constant block that's giving you constants that are equivalent to kilobyte, megabyte, gigabyte, terabyte, petabyte, and so on. So down here in our main program, what I've done is initialize the file size to some arbitrary value, and then I've got this printf statement, and this is basically going to format our result to print 2 decimal places, and then the literal string GB afterward. So this string here is basically saying I'm expecting to format a floating point number, and I'm going to give it 2 decimal places. This GB is a literal GB that's going to be printed in the result, and then we've got the value that's going to be used to fill this in, and that's going to be file size divided by the GB constant. Now you notice this constant block is set equal to 1, and then we're going to bit shift that value 10 times iota. So the first time we're going to bit shift 10 times 1, so we're basically going to multiply this by 2 to the 10th, and then we're going to multiply by 2 to the 100th for the megabyte, and then 2 to the 1000th for gigabyte, and so on. So when we run this, we get a really convenient way to format an arbitrary file size into a human-readable format. And in the Effective Go article, it actually shows you how to put a switch block, which we haven't talked about, so you can make a decision about which constant you're going to use based on the size of the incoming value. So here we get this nice way to format this relatively difficult number to read to be the very easily read 3.73 gigabytes. Now, another thing that can be very valuable to do is using bit shifting in order to set Boolean flags inside of a single byte. So if I paste this example in, we can see an example of that. So let's just say that we've got an application, and that application has users, and those users have certain roles. So inside of this constant block here, I'm defining various roles that we can have. So for example, you might be an admin, you might be at the headquarters or out in the field somewhere, you might be able to see the financials or see the monetary values, and then there may be some regional roles. So can you see properties in Africa? Can you see properties in Asia, Europe, North America, or South America? So in order to define these constants, what I'm doing is I'm setting the value to 1 bit shifted by iota. So the first constant, isAdmin, is 1 bit shifted 0 places, so it's a literal 1. The second one is 1 bit shifted 1 place, so that's 2, and then 4, and then 8, and then 16, and so on. So what I have is each one of these constants is going to occupy 1 location in a byte. So down here in the main program, I'm defining the roles in a single byte, and I'm ORing together isAdmin, can see financials, and can see Europe. Now, if you remember, ORing is going to be set to true if one of the values is true or the other one. So isAdmin has the binary representation of 00000001. I think that's enough zeros. 7 zeros followed by 1. Can see financials is going to end up with 100. Can see Europe is going to end up with the value 100000. And so when we OR those all together, we're going to get this byte that has these 3 flags set to true. So when we run this, we see that we've encoded 8 access roles for a user into a single byte of data. So we're able to store this information extremely efficiently. So if I want to see, for example, if this user is an admin, I can go ahead and print isAdmin and then print out the value. And then in order to determine if that's valid or not, then I can do a little bit of bitwise mathematics here. So I can take the constant isAdmin and that with the roles, and what that's going to do is that's going to apply what's called a bit mask. So only the bits that are set in the isAdmin constant and a roles are going to be left as true, which means if we're an admin, we're going to have the value 1 set at that first bit, and then I can compare that to the isAdmin constant. So when I run this, if we have the admin role, then we're going to get the value true. Now if I check something that I don't have the role, so let me go ahead and copy this down, and then let's just see if they're at the headquarters. So we'll put that in here, and it's exactly the same bitwise operations. We're just changing our mask. If we run this, we see that isHeadquarters equals false. Actually, let me put in my line return here, and then run this again. And you see that isHeadquarters equals false. So we can very quickly and very efficiently store a lot of different information about what roles and access rights a user might have in a simple byte. And having this constant defined with this enumeration expression makes that really fast and really efficient and really clear in our application. Okay, so let's go into a summary and review what we've talked about in this video. Constants are another one of those foundational elements that's going to be a part of almost every application you're going to write. Now, the first thing that we learned about with constants is that they're immutable, but they can be shadowed. So we can create a constant, we cannot assign a new value to it, but if we create a constant on an inner scope from an existing constant, then not only can we change the value, but we can even change the type, because that inner scope is going to shadow the outer scoped constant. They have to be replaceable by the compiler at compile time, so the value must be calculable. So we're not going to be able to access functions or command line arguments in order to determine the value of the constants in our application, but we are going to be able to do simple expressions like we talked about in the enumeration section. They're named like variables, so if you want to export the value of a constant outside of your package, then you're going to use Pascal casing, and if you want to leave it as an internal value to the package, then you're going to use camel casing to name that constant. Typed constants work just like immutable variables. So you can use them in arithmetic operations, you can pass them into functions, but they can only interoperate with the same type. Untyped constants have a little bit more flexibility. So they work just like the literals. So if you replace that constant throughout your application with the literal value of that constant, that's how it's going to work. So that's going to allow it to interoperate with similar types. So we had the value 42 defined as an untyped constant, and we could add that to an integer 16, we could add that to an integer, we can add that to a uint 16, any of those would work because the literal 42 will work in all of those cases. Then we talked about the enumeration types that we can work with, and we learned about the special symbol iota that allows us to start with the value 0 and increments one time every time we use it inside the same const block. Now the one thing that we have to watch out for is that constant values that match the 0 values of variables can cause subtle bugs in your application because you might have logic that you expect to initialize the value of the constant, and if something happens and that initialization doesn't occur, then you're going to be working with the 0 value, which might give you a false match to a constant that you're evaluating against. Using that iota operator, we can actually create what are called enumeration expressions. So we can define the value of the constant dynamically by combining iota with any arithmetic, bitwise operation, or bit shifting operation that's allowable with the primitive type that the constant is representing. Okay, so I hope you enjoyed this video. Again, like I've said before, if you have any questions, please leave that down in the comments below. I'd be happy to dig in and try and answer those for you. Until next time, this is Mike Vansicle wishing you happy gophering.